Hello and welcome to this series of videos. In this series of videos, we're going to be talking about gas transport. And in this particular video, we will be talking about the solubility of gases. Okay, so far in our discussion of the respiratory system, we've talked about ventilation, the act of ventilation, getting air into and out of our lungs. We haven't yet addressed gas transport, which tells us about what happens to those gases that come into and out of our lungs. How do they exchange with the blood? How do they reach our tissues, etc.? That is what we are going to address here. Okay, and we're going to start by looking at this figure, which shows the interface between the alveoli and the surrounding capillaries. Okay, what you can see is that in order for a gas to get into or out of the blood, there are a couple things that need to happen. Okay, so first we need to dissolve that gas in a liquid. And then secondly, we need to cross several membranes. So you can see these membranes here. Okay, so we're going to start by talking about this process of dissolving the gas in the liquid and the factors that affect that. Then we're going to move on and talk about the factors that affect diffusion, the diffusion of gases across membranes. Okay, so starting with this figure, the movement of gas molecules from air into a liquid is going to depend on two things. It's going to depend on a pressure gradient, and it's going to depend on the solubility of that gas in the liquid. Okay, and that concept is embodied in Henry's law, which states that the concentration of a gas in the liquid is equal to the partial pressure of the gas in the surrounding air times the solubility of that gas in the liquid. Okay, I do want to point out that the number that you get out of this is going to describe the equilibrium state. Okay, so this concentration that you end up with is going to be the concentration that you end up with after equilibrium is reached. All right, so taking a look at this figure here, let's imagine what's going to happen, right? So we have air that has a PO2 of 100 millimeters of mercury, and then we have water here with a PO2 of 0 millimeters of mercury. Which way is oxygen going to move in this scenario? Think about it for a second. Okay, so hopefully that wasn't too tricky for you. Oxygen is just going to follow its pressure gradient from the higher pressure to the lower pressure, which means that it's going to dissolve in the water. Okay. However, I do want to point out that the amount of oxygen that dissolves in the water is going to be governed by the solubility of oxygen in water, right? So notice we are at equilibrium here. However, the actual concentrations of oxygen in the air and in the water are not the same, right? So here we have a concentration of 5.2 millimolar. And then down here, we have a concentration of 0.15 millimolar, okay? And that is because oxygen has a low solubility in water, okay? If we compare different gases, we will see that they have different solubilities in water, right? So we just saw in the previous slide that if we have a PO2 of 100 millimeters of mercury here, we're going to end up with a concentration of O2 equal to 0.15 millimolar, okay? However, if we look at that same situation with carbon dioxide, okay, carbon dioxide has a partial pressure of 100 millimeters of mercury in this example. Notice that that is the same partial pressure that we have over here. However, if we look at the actual concentration of carbon dioxide that we see in the water, once this system has reached equilibrium, we can see that it is much higher. than the concentration of oxygen here, right? So we have a carbon dioxide concentration of 3 millimoles per liter and a concentration of oxygen of 0.15 millimoles per liter. The reason for that is because carbon dioxide has a higher solubility in water than oxygen does, okay? Exactly how much more soluble is carbon dioxide than oxygen? See if you can calculate that. So I'll give you a moment, hit pause if you need to. Okay, so hopefully you figured out that carbon dioxide is 20 times more soluble in water than oxygen. And to arrive at that figure, we just can divide 3 millimolar by 0.15 millimolar, and that'll give us 20, okay? Okay, so just as we refer to gases as having partial pressures in the air, we can also refer to gases as having partial pressures in water or any other liquid, okay? The partial pressure of a gas in a liquid, like when we use that terminology, what we really mean is we mean the concentration of the gas, of that gas in the liquid when it has reached equilibrium with the air at that partial pressure, okay? So just to illustrate that, what I mean by that is here we have a partial pressure of oxygen of 100 millimeters of mercury. It has reached equilibrium with the water, okay? So we have this concentration of O2, 0.15 millimoles per liter, but we also call that a partial pressure of oxygen of 100 millimeters of mercury, okay? So partial pressure of oxygen, 100 millimeters of mercury here. Partial pressure of oxygen is also equal to 100 millimeters of mercury here, okay? Likewise, if we look at carbon dioxide, we have carbon dioxide at 100 millimeters of mercury in the air. It has reached equilibrium with the water. Therefore, when CO2 is at this concentration, 3 millimoles per liter, we say that the PCO2 in the water is 100 millimeters of mercury. Okay, so this is a kind of shorthand that we use to refer to concentrations of gases in the water. The reason we do this is because it's just kind of easier to think about, to use like sort of the same units, so to speak, when we're looking at gases moving in and out of the blood, right? So we're changing phases all the time and we don't want to like change concentrations and things like that. Okay, so notice that this can signify different concentrations for different gases, right? So PO2 is 100 millimeters of mercury, but for O2, that means 0.15 millimoles per liter in the water, okay? Here, PCO2 is the same value. If you look at the numbers, it's 100 millimeters of mercury. However, that actually signifies a concentration of CO2 of 3 millimoles per liter.